them are based on this methodology called gradient boosting machines we talked about last time. So in terms of the ensemble method, so far we talked about two different ways. So one is called a bagging. So in the bagging methodology, and one example is this so-called random forest. So in this case here, we generate random samples of training data sets by sampling with replacement. And for each of the randomly sampled data sets, we train a model. And in the end, we take an ensemble of these models trained based on different types of data sets. So this is called a bagging methodology. So boosting is slightly different. So it's still ensemble methodology, but it's doing a different way. So boosting focuses on how do you get in a predictor better for different types of data sets, for different, not different types, but for different training samples. So for instance, gradient boosting is try to build a model based on the residual of predicted area of previous models. And then, so the next model you try to make the residual smaller, and then gradually you build up the models, make things better and better. So that is a gradient boosting methodology. So today I'm going to introduce another boosting method, something called an ADA booster. So the ADA booster methodology, it focuses on something like this, very intuitive. A lot of people think about this, right? So the idea is that suppose you provided with a set of data sets for classification problem. And for instance, show up this side here, you have labels with minus, you have labels with +1 here. You have a set of samples. So when you build a classifier, if your data is not separable, you expect that you will make some mistakes on some of the subset of data sets here. So the boosting methodology is saying this, well, for the next predictor, what I'm going to do is to reweight those training samples and put more weights on the samples that was predicted incorrectly in the previous models. So by doing it this way, so you can focus on your energy, your efforts on those so-called hard examples. So those examples were not predicted previously. So now I'm going to focus on make those examples correct. So to see what I mean here, let's look at these examples here. Suppose initially all data sets, all training samples are equally weighted. They have equal weight because right now I do not have any model yet. So now start with this equally weighted examples here, and I'm going to build a model, build a classifier. Suppose this is my classifier here, very simple classifier here. And in this classifier, I made 3 mistakes here. So this is a positive example was predicted to be negative, this is wrong. And there are 2 examples here, was incorrectly labeled. So I have 3 examples predicted incorrectly. And then what the boosting method will do is to increase the weight of these incorrectly labeled samples. And that was shown up in the next slide. So in this case here, and I highlight that with this kind of a bigger, plus, bigger, minus to demonstrate that in this case, now those samples here are not treated equal. Instead, these 3 samples have higher weights than the remaining samples. So now we have, weights associated with training data sets here, but those weights are not the same anymore as in the case of the initial data sets. So now you can see that we have samples are the same, but we attach a weight to each individual sample, and those weights are updated in this case. And what I can do next is to retrain a classifier based on these type of weighted samples here. So of course, because those samples are weighted more, so your classifier will force to pay more attention on these examples to make them correct. So this show up in this classifier here. So now I retrain a second classifier based on these new data sets. So the samples are the same, but the weights are different. So in this case here, because they are weighted more, so I build a classifier and try to respect those labels here. As a result, I have a classifier, have decision boundary at this point here. So in this case here, now this samples here are labeled correctly. But now, as a consequence of that, because it's a new classifier, we still make mistakes on some samples. So highlighted in these three here. So what we can do next? Well, we're going to increase weight of these three samples and create a new third data set. So in this third data set here, the weights now, so these three here will be, weights will be boosted up. And as a result, you can see now those weights here are increased and the remaining stays the same. So you have this reweighted samples of that. So now what we're going to do is retrain another classifier based on these new weights here. So that will be a third classifier. So in this case here, so you want to make sure these three samples, more or less has to be weighted more. So you build a classifier, try to make them correct. So now you make a new classifier here. So in this case here, you're still making mistakes, right? So these are correct, these four here are mistakes here. So by doing this repeatedly, you can see that you build a classifier at different iterations. So your different classifier will pay more attention to different subsets of data sets and primarily focus on data sets that were incorrectly labeled from the previous models. What do you do? So then there's one question I have to talk about here. Suppose now you have weights attached to the training samples here. And then some of you might ask here, how do I train a model? How do I learn parameters model now with weights associated with training samples? So it turned out that is actually pretty straightforward. So what we do here is this. We look at our loss function. So suppose we are considering the binary classification examples here. So previously, when samples are not weighted and we have average of a loss of each individual pairs of samples here, and we take an average across all the training sample, that was so-called unweighted average loss we used previously. So now in this new case here, we have weights attached to the samples here. How do we train this type of model? Well, what we can do here is this. We're going to assign weights to individual loss here associated with each data term, each data. So for weights have higher, for samples have higher weights, and the loss will contribute more to the final overall loss here. So in a very straightforward way, just simply say instead of do an equal summation of loss from each individual sample, we weight those individual sample loss by these weights associated with the data samples, W sub I here. So W sub I are those weights here associated with each individual samples. So once you have the loss function here, and you can learn the parameters here using this exactly same methodology we talked about before. Because these weights here are fixed now. They are not parameter, they just fixed constant. So what we're gonna do is to recalculate gradient of this new loss function with respect to parameters, and then learn the parameters based on this weighted average loss. And by doing that, you expect that you will be able to derive a different model. So the model derived from here will be different from the previous unweighted average loss. So hence, you will be able to generate multiple predictors. So similarly, this can be applied. So this is for for logistic regression models or for the SVM models. But you can similarly apply that for the decision tree models. So in the decision tree and for classification problem, what do we talk about is so-called information gain. And so that matters. So the weights here will lead to the changes in terms of how do you calculate the entropy of your samples. And previously, each sample weighted equally. By doing that, you calculate the frequency distribution of whether it's associated with a one label or minus one label. But now you calculate the frequency distribution by taking those weights into account. But after that, everything stays the same. So you can also apply these to the decision tree models. So once you have those multiple predictors here, learn this way, and then you can take a weighted average, weighted combinations of these three different predictors. And combine them, you get a predictor of this type of forms here. And that is the kind of illustrate the main idea behind so-called, this boosting methodology. In particular, the ones I mentioned here, something called add up boosting for classification problem. So it's kind of interesting. in many of these applications, in those error boosting and application domains, and these are individual predictor here, sometimes are called baseline predictor, base predictor. So essentially for weighted examples here, how do you build a model of doing that? So it's very often, interesting enough, it's very often that people use decision trees to build up these baseline models. And in many cases, those are called weak learner because each one of them here, is only solving a specific type of problem. So in this case here, you combine 3 weak learners, and with each weak learner and train based on a decision tree model. And in particular, many people are using the simplest possible decision trees to build those kind of baseline predictor here. And sometimes you can see these examples here. This example is very extremely simple. It simply say, I make a decision based on the features of one variable. And you can see that, choose one variable and make a threshold and classify the sample and so on. And this type of a decision tree is sometimes called a stump. And it's the simplest possible decision tree you could imagine because has only one split, only one, and that tree has only one root node, and the rest of them are leaf node. There's no depth. Depth is 1 in that case. So, however, people find out this type of stump here turns out to be very powerful if you combine them with many of them. If you combine many of the stump decision trees, in the end, you can get pretty good classified models. So this is something called error boosting. I have some pseudo code here, and you can take a look at them if you want to find out some of the details about that. But the main idea is what I just show you. So in this methodology here, you assign a weight to each individual samples, and then you update the weights based on whether this previous predictor can label this sample correctly or incorrectly. If they are mislabeled, you boost up the weights so that next time you pay more attention to those so-called hard examples. So there is quite a bit of theory behind this in the error boosting, and in the machine learning community, people in 10 years ago spent a lot of effort trying to understand what. So first of all, in terms of people first observed empirically speaking, this algorithm works very well. And the second, people are trying to understand why, what's the theoretical basis for this type of algorithm. So in the end, it turns out this error boosting is actually very simple. You can actually understand error boosting in terms of a new loss function. So this type of thinking is kind of interesting. So especially in this class here, we always think about how do you reformulate a model, come up with the learning model based by formulating some loss function. We show that in the case of a logistic regression that is based on negative log likelihood or cross entropy loss. And then also we demonstrate that in the case of the SVM, because the classical presentations of SVM is based on maximizing the margin idea that we talk about. And however, we show that and maximizing the margin, in the end, you can reformulate the SVM problem as simply as minimize a loss function, just like what we did before. And the only difference here is that the loss function associated with SVM is in a different form. And namely, that is in the so-called hinge loss function we showed previously. And researchers similarly demonstrated similar ideas for the error boosting algorithm. And they show that error boosting in the end is actually simply corresponding to a new type of loss function in this forms here. And this loss function, if you look at them here, looks pretty similar to the cross entropy loss, and also in somewhat closely related to the hinge loss function. So this shows this shows a particular functional form of the loss functions here. Y is this labels here plus minus 1. F is this the predictive functions here, or sign function, this predictive function here. And they essentially try to minimize exponential y times f here. So if you now think about what we did previously for the linear models, so f, if the linear model f will be theta times X, right? So you calculate the score, and then you calculate Y times scores of that. And so in this type of a surrogate loss function associated with the error boosting is taking this type of exponentially decaying form. So now if you try to think about it, what is the functional form for the hinge loss? And in that case, we have linear, and then reach a threshold point here, that would be 0. So that would be piecewise linear function for the hinge loss for the SVM. And for cross entropy, it looks pretty similar, look like this. But then in this left side here, become linear as well in the case of a cross entropy. And you can see, in terms of functional form, looks pretty similar to this one. So if you understand that way, you can see that error boosting is not much different from the other methodology, except that it uses the new forms of the loss function. So that's kind of a theoretical foundation there, but many people don't think about it this way. Many people feels better to think about it in this type of thinking, right? This is also somewhat very natural, so which means that I'm going to build a multiple predictor. So for the next predictor, I'm going to build, and I better focus on those hard examples that have not been done very well from the previous predictor. So focus on those examples and then build up on that. So that idea is very similar to the gradient boosting idea. So gradient boosting also similar. It's saying now, well, I'm going to focus on those hard examples. Those examples had not done previously. And but however, for gradient boosting, it's based on the ideas, try to match the residual. And then for the error boosting, try to directly reweight those, update the weight associated with each individual samples. So I use different methodology. The idea is similar. All right, so that's what I want to say very quickly regarding this ensemble methodology. So the method here has been used very successfully before. So before this deep learning field and it emerges, and most of the successful methodology in the machine learning field are based on those type of ensemble methodology. I'll show you one example here. So this is the example used, developed in the Microsoft, I believe, something called a Viola-Jones algorithm for phase detection. So that nowadays, detecting phase becomes not hard anymore. But before 10 years ago, that considered a pretty challenging problem. And nowadays, everyone using those deep learning-based methodology, in particular based on this convolutional neural net models we talked about previously. But before that, people use this type of ensemble methodology to do a phase detection. So in that case, what this particular algorithm is called a Viola-Jones algorithm, is build this algorithm based on error boosting algorithm. And in that case, well, you need to generate features. So people use the very classical features by looking at the textual information across the images. And in this particular application, they use something called a wavelet feature, hard wavelet features, essentially by looking at these patterns, little different type of filtering patterns across the image of that. So by doing that, you are able to extract lots of images from individual, lots of features from individual images of that. So these features are built based on the so-called hard wavelet features here, and this shows you some of the baseline that, but you can make it more complicated by convolve this baseline kind of patterns with each other, and now you can generate more and more sophisticated patterns of that. So these are type of feature generation. Nowadays, we call it engineered features, kind of human engineered features. So we kind of extract features this way. And today we don't do this anymore, right? Because we like to use convolutional model to automatically extract features. Now, however, in the old days, people do use this type of methodology. So the idea is, however, once you have this type of features here, now feature is extremely large because this hard wavelet bases here, you have many of them. Now you can extract features across different spatial locations of the image of that. So as a result, you have an extremely large number of features. And the question is, how do you utilize those features here to build a model to classify whether this image is a face or not? That's called a face detection problem. And then the method was proposed at that time by Viola-Jones algorithm is to use an ensemble of trees using this error boosting algorithm. And in that case, each individual tree is a stump, which means very simple as possible, just one decision based on one of the features of that. But it turns out And they spent a lot of time to make this algorithm, tune the algorithm, turned out it actually was doing very well with very high accuracy, and was very popular before. It's winning solution for face detection before the deep learning field. But nowadays people don't do this anymore. All right. So let's just a summary that we talked about this ensemble methodology. We talked about bagging, gradient boosting, and error boosting algorithm. So to capture different aspects of that. So because I want to spend a little more time on this because this is an important topic here.